to introduce our next presenter, Xiaoji Chen from Uber. Xiaoji is the technical leader of Uber's visualization frameworks team. She turns bits into pixels so that autonomy engineers, machine learning scientists, and the general public can make sense of the massive data generated by urban transportation. She makes tools so that others can do the same. So I will hand over to Xiaoji.
Thank you. Hello, everyone. This is Xiaoji. I wish I was able to attend in person. I don't work in autonomy myself. I work to support those who do, and I hope that this is something of interest to you. I'd like to give you a brief overview of a project that we announced back in February called Autonomy Visualization System, or AVS. In this talk, I'll cover these topics: the problem that AVS is trying to solve, why we're doing it, what it offers, and our roadmap. My job at Uber's visualization team is to turn numbers into visuals or bits to pixels so that researchers, policymakers, and creators may gain insights into urban mobility challenges. Over the last 2 years, we partnered with the Advanced Technologies Group to develop Uber's vision for the future of driverless transportation. Together, we've been building a comprehensive suite of solutions for inspecting, debugging, and exploring information collected from offline and online testing. I've built apps that track tens of thousands of cars in real time and apps that visualize the connection between hundreds of thousands of historical pickup drop-off locations. But the tools that ATG needs are nothing like what I've done before. There is an overwhelming volume of sensor and log data that operators and engineers must see to place a decision made by the vehicle in context. Loading this information at near real-time speed and presenting them effectively is crucial to productivity. There is also a growing subdivision of disciplines such as sensor technology, triage, simulation, mapping, safety, and labeling, all of which needs their own specialized tools. This trend calls for better collaboration, sharing, and even outsourcing support. Working on cutting-edge technology also means that the feature requirements of these tools evolve rapidly. New hardware and new machine learning techniques demand that our visual language and data protocol can quickly adapt to new models. Prior to AVS, we saw a pattern in new self-driving initiatives. It was often the autonomy engineers who put together ad hoc visualization tools by assembling off-the-shelf components. These tools tend to be hard to maintain, inflexible, and generally not cohesive enough as a platform when the team grows. This was that ad hoc tool that Uber ATG used 2 years ago. At the time, it ran on a particular build of Linux, on a particular configuration of hardware, and only worked on the Office network. It suffered from years of patches from every engineering student and researcher who needed to see their own data, with a steep learning curve and a lot of performance debt. When we designed our next generation solution, we did it with a web-first mindset. Obviously, web applications have advantage that they're available on any computer from anywhere. This eventually allowed ATG to effectively grow the team and scaled beyond Pittsburgh. The team were able to bring in web engineers who are specialized in building user interface really well and very quickly. It also allowed us to easily integrate with other web tools and additional data sources such as base maps and task planning systems. The outcome of this effort, AVS, is a new open standard for autonomy data visualization. It focuses on creating a consistent visual language across disciplines for effective communication and decision-making. AVS comes in two parts. One, a protocol for describing and transmitting perception, prediction, and motion planning data called XVIZ. Two, a web-based client toolkit for visualizing XVIZ data called Streetscape.gl. By open sourcing AVS, we wish to break the vicious cycle of each shop strapping together their own ad hoc solution from scratch. Instead, we hope to unite people in this field, empower them with the right tool that solves the right problem, incorporate the best ideas, and build an ecosystem of compatible clients and services together. XVIZ is the data protocol designed specifically for autonomy visualization. Comparing to game engine asset formats, XVIZ puts emphasis on data introspection. It organizes data by semantic streams, associates geometries with objects, and allows for dynamic styling based on object properties. Comparing to widely used robotics formats such as ROS, it decouples presentation from platform. Like a video recording, you can randomly seek on a timeline and understand the state of the world at any given point. The visualization layer can also work across multiple platform versions when new hardware and software components are continuously being deployed. XVIZ is optimized to efficiently transfer over the network. The encoding of data is aligned with what the GPU needs for rendering so that we can minimize client-side burden of data processing. It also comes with a server protocol so that the client can incrementally request more details as the user inspects the dataset. In this demo, you can see the user toggling different streams from a dataset. An XVIZ stream is a series of updates that occur at a specific time with specific primitives. Primitives shown in this log include LiDAR point clouds, camera images, object bounds, trajectories, vehicle speed over time, predicted trajectories, etc. Here is a diagram of how data flows from the autonomy system to the visualization client. AVS offers components that build, validate, and encode source data into the XVIZ protocol. The conversion can be done either offline for static storage and hosting, or at runtime for a streaming service. On the client side, the data is decoded and synchronized into time-based data slices and rendered either in a 3D scene or a declarative UI component. Internally, we have built multiple clients that understand the XVIZ protocol, both on the desktop and in the browser. The open sourced component called Streetscape.gl library is a web-based toolkit that makes consuming and working with XVIZ data really easy. We employ this 80-20 philosophy, that is, we handle the hard problems out of the box, such as data buffering, synchronization, coordinate transformation, 3D rendering, and interaction. This gets 80% of the work done. For the other 20% of your application, we do not dictate how data is presented or interacted with. Instead, we offer the building blocks and customization capabilities to help you tailor the user experience to your own use case. This screen recording shows a web application built with Streetscape.gl. This is a real self-driving vehicle log. Streetscape's components, including the 3D viewer, video, chart, table, popover, HUD, and the playback control all work together here to create a complete experience. When building autonomy visualization software on the web, the biggest concern is always performance. AVS is built on top of years of investment that Uber had in WebGL-powered open source visualization frameworks. These frameworks are designed for and battle tested with over 100 high performance, heavy duty products that power everyday business operations at Uber. The 3D rendering engine in Streetscape, called DeckGL, is widely recognized as the state-of-the-art solution for geospatial visualization on the web, used by Google, Microsoft, Facebook, and companies alike. WebGL grants us access to the power of GPU. While the CPU executes instructions at a higher speed, the GPU is capable of performing repetitive tasks more efficiently by running them in parallel, making standard data transformation magnitudes faster. If you think of visualization as a mathematical transformation of data from bit representation to pixel representation, dealing with a large amount of data points is essentially repeating this transformation over and over again, and GPU is precisely designed for that. WebGL offers shader modules that does common visualization transforms on the GPU. For example, the Mercator projection. Here you see WebGL rendering almost 1 million geolocations, a scatter plot at 60 frames per second. All that the CPU does when you interact with it is to calculate the new map center in longitude, latitude, and zoom level. WebGL also allows us to perform data filtering on the fly. Here we're restyling over 300,000 arcs based on mouse position. Again, CPU only sends the pointer position to the GPU, and the GPU is figuring out what to show or hide. This demo shows WebGL aggregating 4.5 million data points on the GPU. Every time the user zooms or pans the map, it recounts the number of points in each of the tens of thousands of grid cells. WebGL is the engine that powers the web client of AVS. There's this old notion of web applications being limited in capabilities and inferior in performance, and that idea is being shattered left and right these days by the quickly growing, evolving web technology. I invite you to visit the AVS website at avs.auto and try the lab demo. Internally, Uber ATG's autonomous vehicle web platform built on top of Streetscape is the foundation of a collection of web-based applications. The AV log viewer allows our operators and engineers to replay any log on top of a base map with LiDAR and radar data, camera, imagery, object boundaries, and so on from any angle. The user can interact with any object in the scene to reveal even more detailed information. For example, here, time series charts of each object's velocity and acceleration. And the operator can compare this information with the prediction path that the autonomy software produced. Triage operators rely on this to determine what went wrong in a particular takeover instance, and they can tag and assign tickets in the same UI. Autonomy engineers may run a new version of their software in a simulation service and then compare its performance with the existing version by playing the two versions side by side or on top of each other. In this case, you can see a bug fix in the motion planner. This was especially important to the team last year when Uber halted street testing. ATG was able to continue iterating on its technology for months. In the 4 months since we open sourced AVS, we got in touch with over a dozen companies working in the autonomy space and learned about each of their own use case and special challenges. This screenshot is from Foresight AI, a company that built 2D and 3D annotation products on top of AVS. As a team, Uber Visualization is committed to collaborate with the community and grow this ecosystem together. Within this month, we are exiting beta and publishing the official 1.0 release. This version includes a frozen version of the XVIZ protocol, Node.js-based builder and web server, feature-complete web client components, a rollback to XVIZ converter, and an interactive playground application where you may edit XVIZ messages in JSON and see them rendered live. In the near future, we're also adding support for point cloud compression using Draco, new primitive types to address broader scenarios, and continue to improve our examples and documentation. Internally, we use a C++ based pipeline from conversion to builder to server. It is our intention to eventually open source them as well, since C++ or Python are the more common languages used by autonomy engineers. If you are interested, look up our announcement post of AVS on Uber Eng blog, and you can visit our official website, avs.auto. Thank you.
So I think we have time for a question. Any questions? Question? Xiaoji? No question here, so. No. Okay, thank you, Xiaoji.